Okay, so we're recording. We are here to talk about essentially the first homework, but also to plug any particular gaps from chapter 7. In terms of priorities, I think we are better off if I start going through the exercises of chapter 7, and then after I got you started, we can then answer, unless there is a question from Rubinstein or chapter 7 that is just a game stopper and you want to ask it right now. Okay. I posted on Canvas screenshots that these two ones I captured from our conversation on Thursday. So I will not do that again here because, it's there. Hopefully it's understandable. I wrote quite a bit on the slides, so on the board. So check them out, and over the weekend, shoot me a question if they are not clear. Okay? They say that they were clear, but then they heard me speak. That was bonus. Okay, so let me start 7.1.
Oh yeah, that's fine. Mine's on my computer.
Yeah, that's fine.
That's the worst 7 I've ever written. Much better. Okay, so we have preferences defined by this formulation, and he does not say, but we are going to take the consumption set X to be R2 plus. So that means that non-negative amounts of x1 and good 1 and good 2 are allowed, not negative amounts. Right? So first of all, how would one approach that? Let's get kind of a plan of action. It asks, do these preferences exhibit local non-satiation? Then it asks, if these are the only two consumption goods and the consumer faces positive prices, will the consumer spend all of his income? And explain. Okay? Incidentally, for any question on any exam ever, you should also always assume that you're supposed to explain your answer, whether the question says explain or not, right? Especially if it's like a true-false question. Always explain, right? Also, a disclaimer. Odd-numbered problems, exercises, have answers in the back. It's fine for you to read those. They're not complete answers anyway. You should acknowledge you read them, and you should, of course, give me a complete explanation. Much more complete than what the author offers. That should be obvious, but I thought I would say it anyway. Now, how should we approach this? Well, I'm always in favor of drawing pictures, but first of all, the first question, do these preferences exhibit local non-satiation, mean we have to remember a definition. So I think I said in first class, definitions have to be in your mind, all of them memorized, and there is no escaping that fact, unpleasant as it is. Okay? So, what is local non-satiation? Okay, I'm going to answer my own questions to move it forward, but do stop me to save time. But do stop me if there's something I say that's not clear, right? So, local non-satiation says for every consumption bundle, X, and for every epsilon positive, there is another consumption bundle distinct from X, that is within epsilon distance of x and is strictly better than x, right? So we have a geometric problem here, really. We need to draw some indifference curves, get a hold of what does it look like, these preferences, what do they look like, and then start answering the questions, right? And this will be true for 7.2 and 7.3 is the other way around, but you know, we will see. It's also a generally good thing to remember. Always draw a picture. And as you draw the picture, explain it. You may feel a little foolish talking to yourself. Pretend you are teaching someone. If you can do this, instead of drawing some lines and say those are the indifference curves, right? What you really want to do is know every step of the way so well that you could explain it to someone else. So that means you understood it. You can check yourself, because if it doesn't make sense, it will be obvious, because you will not be able to explain it to yourself, and then you'll never forget it. That's another benefit from this. So I'm going to pretend I'm a complete newbie at this, which I was a whole number of years ago, and I'm going to start by making this picture. So I will make two axes, one for commodity 1, the other for commodity 2. And then I will start thinking, okay, how do I make some representative indifference curves? Okay, so battery, okay, good. How do you make a representative indifference curve? Well, you start with some random point. So here's a point. Okay? According to this, now it gives us the strong preference, right? So how would we get the indifference? It would have to be that neither this is true, nor the other direction of inequality is true. So for 2 points to be indifferent, this has to be equal. Does it make sense for everybody? Yes? Okay. Yes? Makes sense? Okay, very good. So, if this is a point, let's call it, well, how about we call it point x? With coordinates x1. Let's actually give it a hat. It's a specific point. I don't want confusion between the symbols I used for the axes and this particular point. Okay? So, what other points in this non-negative orthant have coordinates that sum up to the same amount as the x1 hat bar hat and plus x2 hat? And this kind of thing for some sort of utility function, does it remind you of something from intermediate microeconomics? Let me motivate it with some words about the exchanges that are happening here. They're saying here that if you take a unit of one good, say good 2, and take it away from the amount of good 2 the person has, and give it, take away 1 unit of good 2, but give the person a unit of good 1. Person doesn't mind, right? Is indifferent, right? Because the sum x1 plus x2 remains the same. Yes? Perfect substitutes, right? Except, I'm not sure I should be saying goods here, but we'll come back to that. Commodities, I should have stuck with the original terminology. So perfect substitutes. Now we remember what that looks like? Straight line indifference curves, right? And that is in fact pretty obvious here if we believe that I'm able to draw a line of negative slope -1. Okay? Along this line, every point, let's say I have a point y hat, right? Suppose I have some other point along this line. By the construction of this line, these 2 points are indifferent because the sum of their coordinates is the same. Do we agree? Is that clear for everybody? Yes? Any questions? Okay. I really would love to see everybody. Okay, agreed? Okay, so when I turn around and I ask, look up, I want to know if I'm confusing you or the opposite. Okay, thank you. All right, so that's a typical indifference curve, right? Let us find an indifference curve that makes this person happier than that one. Where should I draw it? What do you think? And I am actually asking.
Shift it to the right, that one.
Okay, if I put it here, right, what would be true about the sum of the coordinates of vectors in that new line? So here, let's put it up. Let's put it up, and in fact, let's make it a different color. Okay. Now, if you take any point z on this, what will be true of z1 plus z2? Will it be bigger or smaller than x1 plus x2? Bigger.
Greater.
Does our friend the consumer like more or less? What does this say? He likes less. It's very strange, but it teaches us that we need to read very carefully the preferences of the person as they are given to us by the exercise. This person considers these commodities bads, not goods. Look, he says the X consumption bundle is preferred to the Y one if and only if the sum of the amounts of the two commodities is in fact smaller. Yeah? So it fails the monotonicity assumption, right? Which is so ingrained that you just cannot believe that that's what the exercise says, but that is what it says. Okay. Any questions on that? So to answer my own previous question, in order to find an indifference curve that is higher in terms of utility level, I need to go down and to the left. Okay? So the way I'm going to indicate this is by drawing an arrow in the direction, well, choosing one that works. And it is not this one. I'll draw an arrow in the direction of increasing utility. That is for me. This isn't a mathematical thing. It's a good trick to remember when you draw, especially if later on we're going to do general equilibrium, we're going to have an Edgeworth box and we'll have an indifference curve here for one person and one over there for the other person. It's good to remember what direction utility increases for both of them. Yes? Okay, so now let's start answering the questions. Did you see, by the way, how I started? It appears that there is no easy way to start this problem. So what do? I go to the basics. Let me draw some indifference curves. It's 2 dimensions. I ought to be able to do it. I know enough about analytic geometry to be able to write down, to draw a line where the sum of the coordinates of the vectors on the line are the same number, right? So that way I start early enough in the logical progression of things so that it is kind of obvious what to do next. Okay, so question. Do these preferences exhibit local non-satiation? Okay, let us test. The definition, to remind you, says, for every consumption bundle, there is some other consumption bundle within some positive epsilon distance of it, possibly small epsilon, but it doesn't matter, positive, that is preferred. Let me then start testing, right? Be careful here. I need to prove it for all admissible consumption bundles, yes? So I need to be particularly careful if there is even one that fails this test. Yeah? So let's take Z, since we have it. Suppose I get an epsilon distance and I draw an open ball, in this case disk, of radius epsilon around Z. Yeah? Can I find, within that, can I find a bundle that is preferred to Z, according to what they told me? The answer is, I hope, obvious. Anything below the red indifference curve is going to serve just fine. Yes? So the green dot indicates that I found something within epsilon distance of Z that is preferred to Z. Do we agree? Does it make sense for everybody? Okay. Now, I'm not going to draw it much smaller because you won't be able to see it and the camera won't be able to see it, but it ought to be convincing that no matter how small the epsilon I choose, I always have room to find one green dot like that. Yes? Okay, so I might, if I were careless, lazy, and too quick, conclude that I'm okay. But you probably are suspecting that there is a reason here that I should be more careful. Does anybody want to suggest some point to check that might create a problem? Now that I showed you what I'm testing.
The other side of the
Sure. Anywhere I start though. Yeah, okay. So here's another point. The thing is, by the way, yeah, if I chose a point here, if that's what you're saying, that doesn't bother me because all I have to do is, having chosen the Z and the epsilon, I need to find one point within an epsilon distance of Z that makes the person better off, right? So if I start here, I'll do the same thing, right? Am I answering your question? Okay, so then where is there a place in this graph that I might have trouble?
At the origin?
Let's try the origin, yes? This is, by the way, why I specified this detail, which the book does not specify, but he's obviously looking for that. So here's the origin. Coordinates 0, 0, right? Okay. So now, suppose I choose an epsilon and draw any ball with radius epsilon around the origin. Okay? Can you see any point in this open disk that makes the person worse off, better off than at the origin? No, because it would have to be, see the indifference curve, if it existed, it really stops there because the consumption set is there, but everything that is allowed, right, makes a sum of coordinates that is larger than 0 plus 0, right? So at this point, the requirement of the definition of the local normalization fails. Oh, good. Computer went to sleep, so I thought it might have stopped recording, but it is recording. So that answers that problem, right? That part of the problem. Yes? I don't think everybody is convinced. Where did I lose you? It's okay? Okay. Everybody okay? Yes? Okay? Okay? All right. Okay, good, good, good. So the second part of this problem is, if these are the only two consumption goods and the consumer faces positive prices, will the consumer spend all his income? What do you think? Given all I just told you. Yes?
I want to say no,
And why would you say that?
because if the goal is to get less of the goods and it's positive pricing, they're going to not spend all their money because they don't want it.
In fact, will they spend any money?
No.
No! With these preferences, if we're going to take them literally as the preferences of the person, right? These are not goods, they are bads. So even if they are the only two commodities, this 0.00 is the global maximum of this person's utility function. No matter what the constraint is. Right? The only trick is we have to worry about if the person faces negative prices. So if one of the prices were negative, right, then we might have an interesting story where he purchases a positive amount, purchases in quote marks, in order to to get and lower the other amount. You wanted to say something.
I want to ask you, how do we get the assumption that consumer says?
I added it. I know he means that. I've seen the answer in the back of the book, and I realized he simply should have said it. Yes? Okay. Anybody else? All right, so I'll leave you with that. You can then fill out the details and write an answer. I gave you something like 80% of the answer now, if not more. Yes? Okay. 7.2, which doesn't have an answer in the back. Okay. I should not have used that red. I'll bring the liquid to clean it later. Okay, so 7.2, a consumer has a utility function. Utility ux1, x2 equals max x1, x2. All right? Then, what is the consumer's demand function for good 1? What is the indirect utility function? What is the expenditure function? These are the questions here. And I see from the clock, we probably will not do much more than the first 3 of chapter 7 in an hour, which is not a bad thing, actually, because that's a pretty substantial chunk of the homework, and plus I don't want to give you all the homework. But mostly emphasizing.
One more hour.
Well, we could do that actually. Close to it. We'll see. But basically, I am trying to teach you, first of all, how to start. Because I know that in the beginning, a lot of people, including the one who came in the morning, are like, I'm lost, I don't know what to do. All right? So I'm going to start as elementary as I can. As elementary as I can. This is not to be embarrassing. I mean, we all start somewhere. Just, if I were to go on a horse, she does horse riding. I would probably immediately not only not know how to handle the situation, but then next thing is I'll fall and break my neck. So we're all new at something. Do not be embarrassed, but know how to start. As simple as possible. So here we have this. First of all, remember. In the previous exercise, I asked you a utility function that looks like x1 plus x2. Does it remind you of something from microeconomics, undergraduate microeconomics? And somebody said, I think you said, perfect substitutes, right? Okay. Now, this one, does it remind anybody anything? If not, that's okay. I'll build it. No? Okay, cool. But guess what I'm going to do? I'm going to draw a picture. I'm going to assume, again, even though it doesn't say, that the consumption set is R2 plus, if only I could draw properly, write properly, but anyway, we all have our problems. So there it is. All right. Now, here's my consumption set. Okay. Let me try to make an indifference curve and kind of begin to understand what it looks like in this preference relation, right? Now, first of all, just to clarify, this notation max of a set that has a finite number of elements in it, like in this case just two of them, is pretty easy, I hope. You look at this number and you look at that number. You choose the one that's biggest, all right? And it doesn't matter which one if they happen to be equal, okay? No calculus, no derivatives, there's just two numbers. You look at them and you choose the bigger one, yes? Okay, all right. Which probably is what makes it harder for students, because you expect to take derivative and put it equal to lambda times the price and do that thing with a Lagrangian, right? And this one doesn't look like you can do that. In fact, you cannot, because this function defined on this domain is not differentiable. So really, you should do something else. Okay? So, let me take a point. How about a concrete example? I know that at least one person in this room really likes concrete examples, and I think we can all appreciate that. So, a completely randomly chosen point, coordinates 1 and 2. And since the red did not play well, I will just stick with this black here, even though multiple colors would have been useful. Okay, so there we go. We have this. I shall find all the points that are indifferent to it. Now, to help me, I noticed something in this formula. Typically, only one of these numbers is bigger than the other. But there is an exception. Along the 45-degree line, the coordinates of points on this line are always equal. So that will be interesting, because then, along the line, no matter which one of these I look at, it is the maximum, which is not true anywhere away from that line. So I draw this, it will help me kind of visually see what's going on and what's the maximum point, right? So for example, this point is to the left, which visually immediately tells me, the left of the 45-degree line, I mean. So this immediately warns me that the 2 coordinate, the x2 coordinate, is bigger than the 1 coordinate. And any points over here will be the other way around. Yes? Okay. So, what is the utility that this point attains? Well, let's look at the formula. We have a formula, right? The coordinates are 1 and 2. The utility is the maximum of these two, therefore the number 2. Yes? Now let us find all the points in the R2 plus, in the non-negative orthant, that attain utility 2 according to that formula. How should I proceed?
Should
Yeah.
parallel to x1 here too before x1 here too.
So he says, how about I go horizontally? As long as the x2 coordinate stays at 2 and remains larger than the x1 coordinate, the utility number is going to be 2. Yes? And then I need to stop at the 45-degree line, because otherwise then the other coordinate will start being bigger. Yes? Okay. So part of the indifference curve containing that point is this. Do we understand it completely? Yes? No questions? Okay. All right, so but let's continue because we only done like one side of it. What should I do now? Where should I continue to draw? All right, Doug, go ahead.
Go straight up.
Up or down?
Uh,
If I go straight up, I'm making the second coordinate bigger again. And then it's more than 2. I want to keep the utility exactly at 2. Right? Right.
So you're gonna go down.
I want to go straight down. If I go this way, until I hit the end of what I'm allowed to work in, right? Do you agree the utility is 2? How do I know this coordinate is 2 here? Well, the 45-degree line tells me, right? This is why I drew it. So I have an indifference curve. Now, where is its upper contour? That is, all those consumption bundles that are at least as preferred to those, or strictly preferred. In this case, with the max, the person does like to have more rather than less. Yes? So I'm going to look up to the northeast, right? So here's the upper contour set of this indifference curve. Does it look like it's a little unusual? What is unusual about it?
It seems like it covers the whole graph.
Oh, well, okay, so yes, it does. Well, it does a lot, not all the whole graph. But your typical story of a contour, image of an upper contour is also going up and up and up and up. So it's unbounded, but that does not so unusual. That.
it's concave instead of convex.
Okay, you're almost right. There is no such thing as a concave set. But it is not a convex set, yes. Now, do we see why? Because I can take 2 points here and there that belong to it, and the interval between does not belong to the set, yes? Why do we care about the upper contour set to be a convex set? Because it satisfies the second order conditions for maximization, and from our first order conditions we're going to get a maximum given the constraint. Well, we already know that there is one reason that we cannot do the Lagrangian, and that is this is not differentiable. Now we have a second reason, right? The second order condition is messed up, So even if we could take derivatives, we would not have the usual tangency solution. Do we agree? Do you understand why? Because the usual solution is like that, right? You have a budget line, and all the preferred things are over there, and all the things you can afford are over here, and the two do not meet. And that's why you are at the maximum, given what you can afford, right? That's not going to work like that here. If I went to draw a budget line here, for instance, it always will leave some of the preferred things below, right? Okay, so I'll show you how to deal with that in a minute, but I want to say some other things first. So we have two problems, right? One is the function is not differentiable, and second is the upper contour sets of this function are not convex. So we will need to somehow deal with that to find the demand functions for x1 and x2, because it asks us to do that. Okay? And then I will take a digression after I show you how to do that to do the same exercise with min, which will be a very, very useful case. But so if I start forgetting myself and starting 7.3, stop me and make sure to ask me to do this with min. Okay? Okay, so I am now going to erase this. And in fact, I'm going to clean up a little bit. Now we know how all the indifference curves will look, right? They're all going to be like this. All of them. And the more I move to the up and to the right, yes, the person is now better off. So if I were to draw my little arrow that I suggested earlier, I then see that utility level increases in that direction. Just for for my own ability to interpret the graph. Okay, so let me clean up. In your notebook, make a new graph. And now, instead of starting with an indifference curve, I will start with a budget. Now, in the budget, the assumptions I'm going to make are standard. I'm going to assume that the prices of good 1 and good 2 are positive, and that the income M is positive. Okay? Now, the prices could be such that P1 is bigger than P2, or maybe P1 equals P2, or maybe P1 is less than P2. So I need to cover all these possibilities, right? So how about I start with P1 less than P2, right? Now notice I haven't put any numbers down, and yet I shall survive and do well. Remember what the intercepts are of a budget line. Well, the intercept on this axis is M over P1, right? Since I've assumed assumption P1 positive, P2 positive, and positive, I said it, I didn't write it, so now I wrote it. Okay. So, for this case, M over P1 is somewhere here. M over P2 should be a smaller number, right? Because we take the same number M and we're dividing by a bigger number. So let's put it, I don't know, here. Agreed? So the budget line looks like this. So with the budget line looking like this, the next step is to start figuring out, okay, where is the maximum of utility among all those points that respect this budget line? Okay? First of all, will this consumer spend all their income? Well, let's examine that and convince ourselves that yes, they will. Suppose the consumer is at this point, okay, which is not spending all the income. Make an indifference curve. Well, again, it will really help to have the 45-degree line. So bring up, go down. Here's the indifference curve. Yep. Could this possibly be the maximum of utility given this constraint? Of course not. What if you go here, for example, where the indifference curve is here, higher than the utility. So the utility increases, and yet the new point I drew is also affordable. It's in the budget constraint. So that first point down here is not the maximum. And for the same reason, this one is neither. Right? So I don't need to bother with any of those points below the budget line. I will only bother with points on the budget line. Okay, so here's a point on the budget line. Is it the maximum? Draw the indifference curve. And by the way, in this case, and the one with the min, indifference curve is not to be taken literally because it's not a curve, right? It has a kink, but that's the standard terminology. Okay, is it a maximum, you think? No, it's not. I can keep going in this direction and, right, keep increasing and increasing the utility until, what happens? I ran out of room right here. Okay? So, at this point, I conclude that as long as this is the case, that P1 is cheaper, is less than P2, then this consumer with this utility is going to consume only X1, the cheaper of the goods, and spend all their income doing that. Okay? So I can start now, I can start writing the demand function. It's not the function, but okay, we'll see. For this, exactly. Okay, so I will have three cases. Either P1 is less than P2, or they're equal, or P1 is bigger than P2, right? And I've done the case of P1 less than P2, right? Okay, so I have an answer here. What is the answer? M over P1 if P1 is less than P2. Everybody agrees? Now down here, if P1 is bigger than P2, I can flip this, right? And my answer is 0, right? Because as you see here, I already see here that the more expensive good is not consumed at all. So the trick is, what do I put here? If the prices are exactly the same, how does it look? Well, let's make a budget. Let's assume that the prices are equal, and let's just economize on notation by writing both as just P, since they're the same number. Let's draw the 45-degree line. Okay? All right, so we did that. Let's find, I mean, we know to look now for the corners of the budget set, right? But it so happens now that there is one indifference curve that goes through both of them. The person is completely indifferent between these 2 points, right? So the answer here is that really this is not a demand function because it's a correspondence. At any P1, P2, and M that P1 and P2 are equal, it takes 2 values, a set. It takes a set value rather than a single value. So I will put here, let's just put that notation there, right? So, oh, come on. Right? The person is completely indifferent between consuming 0 of good 1, because then they will consume M over P of good 2, or consuming M over P of good 1 and consuming 0 of good 2. Right? So now, without saying much, I'm going to write the same thing for good 2. By the way, in this notation, just like in the entire variant chapter, when I write a P here, you're to understand it's a vector, P1, P2, right? And just write, then I have committed the crime of using the same symbol for 2 different things. That's not acceptable. So, general advice for everything you write ever. Never use the same letter for 2 different things. So I did it by accident, and so I corrected it. Okay, so does that make sense? Okay. So that gets you started on this problem, doesn't it? Now then he wants you to find the indirect utility function and what is the expenditure function. Having reached this point and not wanting to do all of it, what I will say is, hey, come on, you have this, put it in the utility function and see if you can make sense of it. So, okay, well, I will start. So, once again, I probably will have to consider the cases P1 less than P2, P1 equal to P2, and P1 greater than P2 separately, right? Since I have them separately here. So, to find the indirect utility function, let me then prepare myself. So first, if P1 is less than P2, right? So what am I supposed to do? I'm supposed to take these x1 P of Pm, the demand so-called functions, and put them in here, right? So for the case of P1, P2, I have max M over P1, comma, 0. Is that correct? And of course, what is the maximum of these 2 things? M over P1. Yes? All right. Now you see what's going on here? Without much explanation, I will write this. And here's your indirect utility function. Notice something neat. The demand functions were not functions, they were correspondences. But the indirect utility function is a function. Takes a unique value in all the cases. Make sense? Questions?
So what's the V, P, and the value of them?
The value?
I'm not sure the V.
Okay, this is the indirect utility function. Which is defined in chapter 7, which we defined a little bit in class on Tuesday. And it is found by putting the optimal amounts of the commodities bought into the utility function. Okay? All right, very good. I like questions. Anybody else with a question? Okay, let's see how this is going. Don't want to go to sleep again. Oh, it's more than 4 gigabytes already. Well, it will be fun to upload. I have really fast connection at home, but I think I need to bring this home. Well, the connection here is fast, but I also want to leave at some point. Okay. I will not say any more. I already showed you how to get the indirect utility function here. From that, I think you ought to be able to find the expenditure function. And if not, shoot me an email. But, come on. You can do it. Now, before I leave this problem, I will do the case of min. Right? This is not that homework, but it is an important thing to consider. It is, in fact, the case of perfect complements. And the change I have to make here is to put min here. Okay? So, perfect complements. By the way, because this is one of my pet peeves in spelling, you want the letter E for perfect complements. If you put the letter I, it sounds almost the same, but it means something completely different. Like your hair looks nice today, or something like that. That's a compliment with an I, when you're being nice to someone. There's no need to be nice or nasty to mathematics. We're talking something completely different, yes? So, E, perfect complements. What does that mean? The perfect example, which you should remember from undergraduate microeconomics, is for most people who are born with 2 feet, 1 left shoe and 1 right shoe are perfect complements, right? Now, why does that work with this formula? Suppose I have 3 left shoes and 2 right shoes. 3 left shoes, 2 right shoes. How happy am I? Well, as happy as having 2 pairs of shoes. That third left shoe I can't do anything with. Let's assume they're different. They all fit me, but they are different colors and so on. Okay? Now, And if I am one of those people that is happy to walk out of the house with 2 different color shoes, and I know people like that, then this formula does not apply, right? Incidentally, that works first as a little joke, and it worked for that. But secondly, it makes you really, really, really think about the assumptions underlying these formulas, right? This is the way you always want to think about the math you use. Bring it down to the basic level and ask, what does it really mean? It will take a few years to reach that level to do that automatically, but start today. There is no time to lose. This is why I recommended Rubinstein's book. It's difficult because he assumes tremendous mathematical maturity, but he questions the assumptions very carefully. He says, what does it mean to say I prefer this rather than I prefer that? Okay? So, perfect complements. If I have 3 left shoes and 2 right shoes, and they're all different color, the 2 pairs of each one of the same color, and the third left shoe is something completely different color, and I don't like to walk outside of the house with different color shoes, then really I have 2 usable pairs of shoes. Hence the minimum. The opposite of the previous case where we had the maximum. Okay? So, I will now want to draw indifference curves to see just how they look. Okay? Alright, so guess what? The 45-degree line is going to be interesting, yes? For the same reason, really, that it was interesting before. So let me draw it. Here it is. Once again, I will start with a randomly chosen point, and I will ask where are the other points that are indifferent to it, and draw the indifference curve. So, here's a point. Now, given what we did before, maybe you can kind of begin to see what I should do next. So, for example, you're nodding understandingly. What should I draw next? Around that point, just locally. Should it be vertical or horizontal?
Should be vertical.
Yes. Any points like so? The minimum is the x1 coordinate, right? So all of these points have the same minimum, and so they are indifferent to each other. Do we agree? Yes? So, for example, this is bigger than that, and so is this coordinate, and so is that coordinate. So the utility of all these points have utility equal to this amount, right? When I hit the 45-degree line, I go that way. Does it make sense? Right? Everybody okay with this? Okay. Here's an indifference curve, and all of them are going to be like that, and the direction of increase of utility is the normal one. Yes? Now then the question is, how do we find demand functions? Because just as before with the max, the min function is not differentiable. So guess what? I will make some pictures. And that pretty much will convince you of the answer if you haven't seen it already, which in your intermediate micro you should have seen, to be honest, but it might be old business by now and you may have forgotten. So let me draw a budget line. I think I can do it down here. It's not too cluttered yet. I started with a budget line that is drawn under the assumption that P1 is less than P2, but I'm not too concerned, because I know where I'm going, I'm not too concerned in writing down the difference P1 is smaller than P2 or whatever here. Because let's see, do I want to consume all my income? Okay, suppose I don't, right? Suppose I am like here. Can I do better? Let's find the indifference curve that goes to that point. And yes, I can do better, for example, by moving there. Right? Basically, though, that tells you the other thing. Any point like here. Now, this one uses all your income. But if you draw the indifference curve, and you discover that the corner of it doesn't use all your income, you're better off moving up and moving up along the 45-degree line until you reach this point. And now you cannot go any further, and you have the maximum. Okay? For those who are eager to have an actual proof of that, you can construct a proof by the separation of convex sets. You don't have to do it for any homework in this class. But there is a formal proof, but I just want to show you how it really works in the picture. This is convincing enough. So the reality is, it's really easy to find the demands here, right? Just set x1 and x2 equal in the budget set, because you need to respect your budget, right? So you say, okay, x1 will be equal to x2. Let's call it whatever, x hat. You put it in the budget constraint. Right? Yeah. And then you get x hat equals m divided by p1 plus p2. Right? So that's for x1 and for x2. So there you go. Now you have the demand, and it's a function. You see, you get the unique value now, and it doesn't really matter if P1 is bigger than P2 or anything like that. It does matter that the P's are positive, so we're not dividing by 0 accidentally, which we can never do. Now, just to continue a little bit, let's find the indirect utility function for that, and then we'll do a little bit of 7.5, and then I think we're going to quit. Okay? So, indirect utility function for this case is, let's see, I need to go to this formula, of course, and substitute for x1 and for x2 the optimal amounts. So, minimum of m over p1 plus p2, m, oops, the comma went in the wrong place. Equals, well, these are always equal. So, m over p1 plus p2. Observe something kind of neat here. We started with a non-differentiable utility function, and we ended with a very simple and eminently differentiable indirect utility function. Right? Okay. Now, if you want, you can go play with the perfect substitutes case, where the utility function is x1 plus x2. But the more, the better you are, not exercise 7.1 with a bizarre situation where you wanted less, right? You will discover, and you should do that, it's fun. Solve it, you will discover that the function x1 plus x2 is about as simple as you can have. It's differentiable, it's very simple. It's going to also hit corners, and you're going to have cases in the optimal demands, and therefore you will be careful in finding the indirect utility function. Okay? The beautiful thing about all of these is, did I do did I even take a derivative? No, I did not. However, I exercised my ability to really understand what is going on in these graphs and about preferences. Because my advice is to always do that. Okay. Any question about this? Right. So let's start variant 7.5. And yes, I know there is an answer in the back, but it doesn't really explain very much. And this is one where a good picture is really important. Okay, part A of 7.5 is Gesundheit. It's a silly question because he forgot that he only gives you the formula, the description, the definition of a quasi-linear utility function in chapter 8. So you open the back of the book and you see it's a quasi-linear function and you don't know what that means. Fine. At least you know it's a quasi-linear function. You don't have anything to explain there. That's a goof of the author. He should have defined quasi-linear before he asked you about it. Part B, however, you can do. And before you can do that, you need, of course, to understand what this utility function is. So what does he tell us? He tells us the utility function, uppercase U, big U, is built up from a little u of x1 plus x2. But x1 is not your usual divisible good. Instead, you can either have zero amount of x1, it says, or 1 unit, and that's it. In a lot of public good models, this is like, do we build a bridge here or do we not? 0 is we don't build it, 1 is we build it. And it doesn't make sense to build 3/4 of a bridge. You build it or you don't build it. Okay? All right. So, what is the consumption space? Okay. We have to obviously be very careful for good 1, because he tells us that's the one that is discrete and not continuous. So, it can be consumed at 0 amount, or it can be consumed at 1 unit, and that's it. So the consumption set is this half line. We also are not going to accept any negative amount for x2, right? So it's this half line union with this half line. And you are forced to ignore any other points. They're not feasible. Okay? So, here we have a case where, for very good economic reasons, you either build the bridge or you don't, the consumption space is not a convex set. Right? Because it's 2 lines, everything in between is missing. And all of the stuff out here is missing. Okay? Does this mean we are hopeless? Oh no, we're never hopeless. If it's an exercise in the book, you know it has an answer. Right? Okay. Plus, we're smart people. We'll figure it out. So, again, what is my next step? Oh, by the way, he gives me some assumptions. He tells me by assumption that you evaluate good x1 its subutility in this little u function here as 0 if you don't have it. And let us assume that the price of good 2 is just 1. You may have heard the expression, we're taking good 2 as a numeraire commodity. Okay? If not, change the units that you measure x2 so it is actually coming at the price of 1. So that's kind of trivial. It's not a big deal as an assumption. Okay. Now, tell me how I build an indifference curve. Here, curve is really the wrong word, right? An indifference set will contain exactly 2 points. And let me show you how you find them. Start here, right? Okay. I want to know, is there any other allocation, consumption bundle, excuse me, in my consumption set consisting of this half line and that half line only that is indifferent to this? So this comes with some amount x2. Okay, all right. And again, since it's a specific x2, let's give it some decoration to denote that. I'm tired of hats, I'm going to make it a prime. It doesn't really mean anything except I need a separate symbol. Okay. Now, what is the utility that this person attains here? Well, the utility here is, so utility of 1 x2 prime equals little u, oops, big U. I'm just putting this formula in action. So little u of 1 plus x2 prime. Correct? So I need to figure out a point over here somewhere that has a utility that is precisely equal to that. Right? Okay. Now, first of all, should I be looking above or below x2 prime?
Above.
Yes. Because what happens is as I move, does he tell us? He didn't actually say that u of 1 is positive. Did he say that and I missed it? No. So let's assume for the moment u of 1 is positive. Assume u of 1 is positive. And after I'm solving this way, you can just go ahead, reverse that assumption and see what happens. It won't be too hard. So now, yes, in order to be indifferent, since I'm losing u of 1 by dropping the consumption of x1 to 0, I need to get more x2, otherwise I will not be indifferent. I will have lower utility. Yes? So I'm going to be somewhere here, let's call it x2 double prime, whatever, and I can in fact tell you how much that has to be. How? Because I know that big U at 0 x double prime 2 must equal big U of 1 x2 prime, right? Lots of symbols, but the logic is very simple. And again, I haven't done a single difficult mathematical thing. The only difficult thing I'm doing is thinking slowly and clearly about things. Then I know it's difficult, but it's not complicated. It's just difficult. Okay. I already calculated this, right? So I have little u of 1 plus x2 prime. And this one is, well, I know u of 0 is 0. So this is, in fact, x double prime 2. Right? That tells me exactly where to put this. Right? And incidentally, now you see, if we had assumed u of 1 is negative, it would immediately tell you that the x2 double prime has to be below x2 single prime. Right? Now you know what it takes for 2 points to be in the same indifference set. They have to satisfy this. Okay? Point 0x2 double prime is indifferent to point 1 x2 single prime if and only if this is true. How do I know? Well, I use the utility formula. That's how I know. They told me that's the utility that represents this person's preferences. Okay? Right? Okay. Based on that, I will let you loose to try the rest of the problem yourselves. Right? So I think you're going to be okay. Right? Now I would, well, if you're not, shoot me an email. But 7.3, I want to say just a few things, mostly because I was a bit hasty in the morning, and I think I might have given the person who was asking me in the morning maybe a misleading answer here. Let us look at 7.3. It says a consumer has an indirect utility function of the form m over minimum of p1, p2. What's the form of the expenditure function, the form of the quasi-concave utility function for this consumer, blah, 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 blah. Now let's see here in the back what he says, and let me see if I can fill in some answers. 7.3, the expenditure function is u of minimum p1, p2. Utility function is simply x1 plus x2. Oh, interesting. That's perfect substitutes. So let me tell you some ways that you can kind of get that answer and confirm it. Right? First of all, I already suggested that you should go and take the perfect substitutes case and find its demands and find the indirect utility and so on as a useful exercise. Now you know extra reasons why it's useful, because it will help you answer 7.3. But you can also do it another way. So, for example, we have some identities in section 7.4. And those identities relate the expenditure function and the indirect utility function. Since he gives you the indirect utility function, and the first thing he asks is, what is the expenditure function? That's supposed to ring a bell in your brain. And the bell should say, I learned some identities that relate these two. Can I use them? So that I will not tell you how to do because, you know, you're smart. You'll figure it out. But that's where you might want to start looking in the direct method of answering this problem at this exercise, solving this exercise. And the other one already I suggested, just take the perfect substitute case and figure it out. And I brought it up because of the beautiful duality of the situation, right? With a beautiful, simple x1 plus x2 function as a utility function, the indirect utility function is not that beautiful and simple. Well, I don't know if it's beautiful, but it's simple, not as simple as just summing two numbers, right? And the other way around, if you have perfect complements. Okay? And logically speaking, that's particularly satisfying because perfect complements in the logical sense of what goods are and how they relate to each other is exactly the opposite case of perfect substitutes, right? All right, stopping this before it becomes even more gigantic.